Greetings to everyone. My name is Jose Escobar. I will talk about the midterm project of the operating system subject. To have a context of what needs to be solved, we must know the problem. The company, XYZ Electric, requires a system that allows measurement between objects to avoid vehicle collision. To do this, a laser and a gyroscope are available. Based on the data generated by these sensors, the real distance must be estimated with the least amount of lost data and in the shortest possible time. The vehicle can have some inclination, causing that the measured distance is incorrect. As it is observed in the second illustration, d is the real distance, but d prime is the measured one. So d prime is greater than d. That's the problem that we need to solve. The solution I propose is through concurrent processes. There is a parent process called P that has three child processes, S1, S2, and C. S1 reads the laser data, S2 reads the gyroscope data, and C performs the distance calculations. The parent and the child sensors have a signal handle. P uses to start a specific sensor that is not active, and the sensors uses to stop or restart. The processes are independent, which means that the execution of one does not affect the execution of the other. These processes need to cooperate to communicate data and perform calculations. This is achieved by sharing a resource using inter-process communication or IPC. In this case, the shared memory model is used, and the resource to be shared is a structure containing an array and a semaphore for process synchronization. As mentioned before, S1 and S2 are in charge of the sensor's data. They read and write those values in a given array index. Then C reads those values and estimates the real distance using the formula d prime times cosine of alpha. The project was developed in such a way that new sensors could be added. The only thing that will have to be modified are the calculations that will be made with this additional data. Processes can easily handle signals compared to threads. Since each process has an identifier, signals can be sent to a specific process so it can handle them. I did not use threads because they make things a little bit more complicated. For example, we must declare which signals will be blocked and which will be handled by each thread. Threads and signals are tricky in a way that unexpected behavior could happen. Additionally, separating one process into several ones can help reduce failures and bugs. As I mentioned before, each process is isolated from the other, so if one sensor fails, the rest will not be affected. Now I will show you the results. Once the system was implemented and tested, the following results could be obtained and are reflected in the graph. We have a concurrent version using processes, that's the green one, and a non-concurrent version, that's the blue one. The graph shows the time it takes for each version to process a fixed amount of data. In this case, the x-axis shows the set of data that will be used for each version, and the y-axis shows the time it takes to process that set of data. And as you can see, the time it takes using concurrency is less than the time not using it, as it was expected. It can be said that on average the concurrent version is 1.34 times faster than the non-concurrent version. It is important to note that the difference in time between versions increases as the size of the dataset increases. For example, when there are 10 data, the difference in time is 7, but when there are 50 data, the difference increases to 28. Here is another graph in which you can observe the behavior of the version as the data to be processed increases. And as mentioned, the non-concurrent version has a higher growth than the concurrent version. One way that I think the system could be implemented to optimize more time and resource is through threads. The communication between threads is simpler than doing it between processes. That's because the address space is shared and, consequently, less memory is required. Additionally, context switching and creating a thread is less expensive than doing it with a process. It is possible to combine the processes with threads to perform more operations in case the system grows. For example, if we need to add more sensors and do more calculation, then it's a good idea to add threads to those processes so the result can be obtained and much faster. So here I conclude my presentation of the project. I hope everything was clear, and thanks for your attention.